Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Welcome everybody to the UW CSE Colloquium. It's my great pleasure to introduce Ani Majumdar. Ani is currently finishing up his PhD at MIT, where he works with Russ Tedrake. His research is in robust control, mostly focusing on unmanned aerial vehicles. Whereas like 5 minutes ago, we already showed that he can also do robust control on laptop displays. And the idea of his work is also a lot on like how can you break down a large-scale control or planning problem into smaller pieces and then also stitch them together so that you can still prove safety, for example, of the overall controller. And he won several awards for his research, and most importantly, he won the Best Paper Award at the 2013 ICRA conference, which is the main robotics conference. So his paper was chosen as the best one out of at least 2,000, I think, was kind of the number of papers. And today, he'll give us an overview of his research. Thanks.
All right, thanks very much, Dieter. So today, I'm going to tell you about my research on controlling highly agile robotic systems in a way that allows us to make formal guarantees on their safety. So probably a lot of people have heard about Amazon's Prime Air. So this is their proposed drone delivery system, where the idea is when you order a new package from Amazon, one of these unmanned aerial vehicles, UAVs, that you see in the picture here, will come and deliver it to your doorstep within just a couple of hours. In general, there's been a lot of excitement around the UAV industry. So for example, a number of companies have announced projects and products for a wide range of different applications, from mapping cities to doing aerial photography, for instance. So while these developments are extremely exciting as a roboticist, and also from a consumer perspective, it's maybe not quite so exciting if you're the FAA. So the Federal Aviation Administration is extremely concerned about these kinds of developments. So currently, they're used to having just a handful of crashes for millions of hours of operation for commercial airliners. But introducing this kind of autonomy into the loop represents a fundamental shift in the way we need to think about safety and also regulation and certification. So probably a lot of people have this really scary image of thousands of these things flying over our heads, running into things, falling out of the sky. And this challenge of safety is a real concern. So there are a number of factors that exacerbate this challenge. So the first is that we expect these systems to operate in very cluttered environments. So for example, in urban environments or even close to human beings. We also demand speed and agility on behalf of these machines. So there's no point having a drone delivery program if it takes more than a couple of hours for the system to get to your doorstep. And finally, these systems must also be able to deal with unexpected events in the environment. So things like wind gusts, for example, or unexpected obstacles that show up in front of the robot. So it's worth pointing out that these challenges are not restricted just to UAVs. So we face many of the same challenges in a whole range of other robotic applications. So for example, humanoid robots doing search and rescue missions, or factory robots working close to human beings. So these systems must also be able to operate safely while being fast and agile and responding to unexpected events in their environment. So from a theoretical perspective, these applications pose a number of fundamental challenges. So what we'd ideally like to be able to do is formally guarantee safety, so formally guarantee that the robot will operate safely. So for a UAV, this essentially means not crashing into obstacles and not falling out of the sky. But there are a number of technical factors that make this goal extremely challenging. So the first is that the dynamics of these systems can be extremely complicated. So for example, we might have high-dimensional state spaces that we might need to reason about, and also potentially nonlinear effects, such as aerodynamic effects. There's also significant uncertainty in the dynamics. So for example, things like wind gusts or an uncertain payload that the robot might be carrying. And finally, there's also significant uncertainty in the geometry of the environment. So typically for these applications, we don't know where obstacles will be and what they'll look like until the robot actually starts operating in that environment. So what I'll present today, I believe, is a partial solution to this ideal goal of guaranteeing safe operation of the robot, despite having these technical challenges. So just to keep the discussion relatively constrained, so for most of the talk, I'll focus on the problem of high-speed UAV flight through really cluttered environments. But I want to point out that the approach that I'll present is significantly more general and not tied to the specifics of UAV applications. So I'll present algorithms for designing feedback controllers that come with associated guarantees on their safety. And I'll then discuss how we can take these feedback controllers and certificates of safety and use them for safe, real-time planning in environments that the robot hasn't seen before. And along the way, I'll present a number of hardware experiments on a small fixed-wing airplane flying at high speed through very cluttered environments. OK, so here's the general problem we're trying to tackle. So what we want to do is be able to guarantee that the UAV will fly through some environment without collisions, given no prior map of where the obstacles in the environment are. So I'll make a number of assumptions. So first, I'll assume that we have a reasonably accurate model of the dynamics of the system. So it doesn't have to be perfect, but I'll assume that you have a model of this uncertainty in some parametric form, and that this uncertainty has a bounded effect on the system. And finally, I'll assume that the robot is equipped with a number of sensors which report where obstacles in the environment are, but in some finite horizon in front of the robot. OK, so instead of discussing the solution to this completely general problem, for most of the talk today, I'll focus on what I consider to be the most important subproblem, which is how do you plan a single maneuver such that the UAV is guaranteed to be collision-free when that maneuver is executed. So here's the picture I want you to have in your head. So suppose the robot is flying along, and suddenly its sensors report a number of obstacles in front of the robot. The question is, how do you plan a single maneuver such that you can guarantee that when that maneuver is executed, the robot will remain collision-free? So let me give you some intuition for some of the technical challenges involved with this task. So first, there's a combinatorial decision that needs to be made. So should the robot go left around the obstacles? Should it go in between the obstacles? So there's a discrete number of possibilities that it needs to choose from. So we also need to take into account likely tracking error. So for instance, the current state of the robot might not be perfectly aligned with the plan that the robot made. And more significantly, we also need to take into account the effect of uncertainty or disturbances on the system. So for example, there might be a large wind gust that blows the airplane off its planned trajectory and makes it crash into an obstacle. So what we really need to do is reason about the funnel of possible outcomes that the robot might be driven to, depending on what value the disturbance takes. So different maneuvers also have different susceptibility to disturbances. So for example, it might be a lot easier to fly straight. So in particular, the set of possible outcomes that the robot might be driven to might be a lot narrower, as opposed to doing a really aggressive turn to the right, where you're more exposed to a large wind gust that can blow you into some large set of possible outcomes. And finally, all of these decisions need to happen in real time. So real time for these kinds of applications means just small fractions of a second. So there's been a lot of work in the controls and robotics literature addressing some of these challenges. So a lot of the early work and also some more recent work has focused on the problem of doing robust kinematic motion planning. So cases where the dynamics of the system are not dominant and it's purely a geometric problem that you're interested in. So in cases where the dynamics of the system are really important, there's been a lot of work under the umbrella of planning under uncertainty. So the basic idea here is to model the dynamics of the system probabilistically and reason about how probability distributions evolve through your dynamics. There are a number of challenges here that I want to point out. So the first is that this problem of propagating distributions through nonlinear dynamics is computationally a very challenging one. So typically, you're forced to make certain approximations, which makes it really hard to make any kind of formal guarantees on what the system will do. So slightly closer to the set of assumptions that I've made here is the work on computing reachable sets, for example, using the Hamilton-Jacobi-Bellman equation. So these reachable sets are essentially what I was calling funnels on my previous slide. So it turns out for linear systems plus bounded uncertainty, computing these reachable sets can be done very efficiently. But for nonlinear systems with uncertainty, computing these sets is computationally a very challenging problem. So it's worth remembering that even though many of these illustrations or plots that I'll be drawing will be in 2 or 3 dimensions, these sets really live in the full state space of the system, which for a UAV is 12-dimensional. So we need to think about the x, y, z position of the robot, the roll, pitch, yaw, and also the time derivatives of all of those numbers. And computing these sets in that kind of high-dimensional space is computationally very challenging. And typically, the AJB methods have trouble scaling up beyond about 5 or 6 dimensions in the state space. So the approach that I'll present today will have a starting point in a different set of literature within the motion planning community. So in particular, there'll be 2 phases. So there'll be a computationally intensive offline phase and a really efficient real-time phase. So in the offline phase, what I'll do is first compute a trajectory library for the system. So this is essentially a set of maneuvers that the robot knows how to execute. So things like fly straight, turn left, bank right, and so on. So this kind of trajectory library idea has been really widely used in some of the most successful robotic systems that have been deployed that need to plan in real time. So what I'll do next is augment this trajectory library with a number of feedback controllers that correct for local deviations from these trajectories. And for each one of these trajectories and associated feedback controllers, I'll compute funnels around each one of them. So here are 3 examples of what funnels look like for a UAV system. And what we'll be able to guarantee is if you start off in the inlet of the funnel, so the initial condition of the funnel, and if you execute one of these maneuvers, you'll be guaranteed to remain within the funnel for the finite duration of that maneuver. And I'll describe some of the computational techniques or machinery we use for computing these funnels in just a little bit. So in the real-time or online phase, when you actually start seeing where obstacles in the environment are, the basic idea will be to search through this pre-computed library of funnels and try to find one that's collision-free. So in particular, if you're able to find one that's collision-free, then this guarantees that when this maneuver is executed, the robot will remain collision-free. Because if the funnel doesn't intersect the obstacles and the robot is guaranteed to remain within the funnel, then the robot won't collide with any of the obstacles. OK, so that's the high-level approach. Let me now dig into some of the details of the approach. So in the offline phase, what we'd ideally like to be able to do is, given a control system of this form, we'd like to design a feedback controller that minimizes the size of the funnel going forwards in time. So I'll fix the set of initial conditions, and I'll try to design a feedback controller that minimizes the effect that the disturbances have on the system. So let me actually first start by describing something that might be much more familiar to people in the audience. So probably a lot of people have heard about Lyapunov analysis in the context of proving asymptotic stability of nonlinear systems. So let's say you're given a dynamical system of this form, x dot equals f of x. So let's say the controller is completely fixed, so the dynamics just depend on the state. Let's say we want to prove that for any initial condition in this gray region that I've drawn, this initial condition will asymptotically approach the origin. So one way to prove this is to find a Lyapunov function. So a function v for which the gray set that I've drawn here is a sub-level set of this function. So sub-level set just means all the states x for which the value of the function is less than or equal to rho. So rho is 100 in this picture that I've drawn here. And let's say we can further show that the value of this function is positive definite on the set, and the time derivative is negative definite. So in other words, along trajectories of your system, you're going downhill on this function. So intuitively, it should be clear that if your function looks sort of like a bowl and you're going downhill on this function, then you'll asymptotically approach the origin. So you can use a similar kind of idea for computing funnels. So we'll represent the funnel as a sub-level set of this time-varying function v. So in this case, what we're interested in is not asymptotic stability. What we want to show is invariance. So in other words, we want to show that if you start off, so the state of the robot starts off in this initial condition set, so the inlet of the funnel, then when you execute this maneuver, you'll remain within this time-varying sub-level set. So you can write down a slightly different Lyapunov condition in this case, which says that when v equals rho, so in other words, when you're on the boundary of the funnel, v dot is less than rho dot. So essentially, the vector field is pointing inwards when you're on the boundary of the funnel. So if you start off in the funnel, you never leave it. So in the kinds of applications we're interested in, it's really important to take into account the effect of disturbances or uncertainty on the system. So it turns out you can do a similar kind of analysis for cases where you have bounded uncertainty. So what we'd like to show is this invariance condition for bounded uncertainty. So we want to show that when you start off in this initial condition set and you execute this maneuver, no matter what the disturbance is in some set of disturbances that you care about, you'll still remain within this funnel. So the Lyapunov condition you can write down here is essentially the same as before, except now you impose it for all possible values of the disturbances that you care about. So we're essentially doing a worst-case analysis by finding a common Lyapunov function. OK, so I've written down these mathematical conditions for funnels, but the big question is how do we actually put these on a computer? So the first thing we'll do is restrict the dynamics of the system to being polynomial. So this might seem like somewhat of a restriction, but in practice it turns out not really to be the case. So for many of the robotic systems we encounter in practice, relatively low degree, potentially time-varying polynomial approximations do a good job of capturing the main nonlinearities. And moreover, for many classes of systems, such as most rigid body systems, you can do some clever variable substitutions to turn the dynamics into a polynomial. But unfortunately, as we show in this paper here, checking this invariance condition that we need for funnels and checking many other similar conditions, these problems are all NP-hard for polynomial dynamical systems. So the next observation is that these Lyapunov conditions that we're interested in are essentially checks on non-negativity of functions. So we're interested in checking things like v greater than 0 for all x, v dot less than 0. But again, unfortunately, even for polynomial functions, checking non-negativity is an NP-hard decision problem. So the idea behind sums of squares or SOS programming is essentially to check a sufficient condition for polynomial non-negativity, which is that your polynomial is a sum of squares of other polynomials. So this is clearly a sufficient condition for your polynomial being non-negative for all x. And it turns out you can do this pretty efficiently using semidefinite programming, which is a particular kind of convex optimization problem. So this idea goes back to Pablo Perillo's PhD thesis, and it's been really widely used in the controls literature for doing Lyapunov analysis for nonlinear systems. So there's one final thing I want to point out on the slide, which is that we're really more interested in conditions of this form. So we want to say that when our state x belongs to some set f, then v dot is less than 0. And it turns out you can impose these kinds of conditions also using sums of squares programming. OK, so let me give you some more details on SOS programming. So I want to make sure that people at least get the main idea behind it. So polynomial p being a sum of squares is equivalent to me being able to write it down in this form. So if you can write it down as v transpose qv, where v is a vector of monomials. So it essentially contains products of your variables in x up to degree half the degree of your polynomial. And q is a positive semidefinite matrix. So this is the condition that makes this a semidefinite programming problem. So this allows you to check if a polynomial is a sum of squares. So if you hand me a polynomial, I can go try to find a matrix q such that your polynomial equals v transpose qv, and this would certify that your polynomial is a sum of squares and hence non-negative. But more importantly for us, we can also search over the space of sums of squares polynomials up to some bounded degree by searching over positive semidefinite matrices q. And this is basically what allows us to search over the set of Lyapunov functions when we're computing funnels. OK, so going back to the original problem I started off with, you can also do feedback control synthesis with this kind of idea by searching for a Lyapunov function and a feedback controller at the same time. Yes, go ahead.
Is there a sense in which the sufficiency is somehow like right? Like my version CS theory, right? These SOS things are, you know, the hope is if you can't do it there, there are other methods that will work.
So yeah, so the question is essentially, is there a gap between sums of squares and non-negative polynomials, right?
Or what other techniques you might do, like the sense in which this is the best you could hope for under
Okay. So I guess there's some complexity theoretic reasons maybe for believing that sums of squares is the most efficient way you can do this kind of problem. Yeah, for checking non-negativity. But I mean, they're still in the conjectural stage, right? So I think they depend on the unique games conjecture and things like that. But there's no real unconditional proofs for showing that sums of squares is the best in any sense. But there's still a gap between sums of squares and non-negative polynomials. So especially as the degree of your polynomials grows and also as the number of variables grows, in some sense
But are these control problems like general non-negative polynomial problems, or are they more structured?
Oh, I see. So again, I'll just repeat the question just to make sure people can hear. So the question is, are these control problems very structured sums of squares problems, or are they completely unstructured? So yes, they do have quite a bit of structure. So especially if you have symmetry in your dynamics or sparsity in your dynamics, oftentimes you can exploit the symmetry or sparsity to make your sums of squares programs smaller and cheaper to compute. Okay, so as I was saying before, unfortunately, it turns out that doing this joint synthesis of feedback control synthesis and Lyapunov functions is not quite a sums of squares program. But it turns out if you fix one of these decision variables, so if you, for example, if you fix the Lyapunov function, you can search for a feedback controller using sums of squares programming. And similarly, if you fix the feedback controller, you can search for the Lyapunov function using sums of squares programming. So the basic idea here is to just alternate between these two sets of decision variables while trying to minimize the size of the funnel. Okay, so I've described these computational techniques for computing funnels, but probably one question that everyone in the audience has is, do these computational guarantees really mean anything on a real challenging hardware system? So the hardware system I'll present experiments on will be the small fixed-wing RC airplane. So I spent a lot of time doing system identification for the system to get an accurate 12-state dynamic model for the system. So I'm basically treating the system as a rigid body subject to aerodynamic forces, where the lift and drag coefficients for the aerodynamic forces come from a flat plate model plus a small correction term. So I refined this parametric model that I had using lots of data from flights. So I ran the airplane with different open loop control inputs and did simulation error minimization to refine the parameters in my model. And I was also taking into account some parametric uncertainty in the model, which I decreased as I collected more data and as the model improved. So it's worth pointing out that I'm hiding essentially months worth of work here in this one bullet point. So it took a lot of time to do this system identification, but I won't say too much about that here unless people ask me at the end. So the experiments I'll present will be in a motion capture arena, and all the computation is on an off-board platform. So here's a visualization of what the funnels look like. So it took about 30 minutes on a standard desktop computer to compute this funnel. And again, it's worth remembering that even though these visualizations will be in 3 dimensions, the funnel really lives in this full 12-dimensional state space of the system. And I'm just projecting down the funnels onto 3 dimensions in order to be able to visualize it. So here's a video of what it looks like when the airplane flies through the funnel. So I hope you enjoy these visualizations, by the way. It took me about 2 weeks to make. Okay, so from these videos, it looks like the airplane is remaining within the funnel as you would expect from sums of squares programming. And I did a number of thorough experiments to actually validate this. So in particular, I did 30 flights from different initial conditions, starting off within the inlet of the funnel. And all 30 of these trajectories remained within the full 12-dimensional funnel. So here's a plot that shows that. So what I'm plotting on the y-axis is the value of our Lyapunov function as a function of time for each of these 30 trajectories. And I've just normalized things so that the one level set of the function corresponds to the boundary of the funnel. So essentially anything less than 1 is inside the funnel, anything greater than 1 is outside. So as you can see, all 30 of these trajectories start off in the inlet and then remain within the funnel as you would expect and hope from sums of squares programming. So these computational guarantees that we were computing on our computer actually translate onto the real hardware system, which is quite nice. Okay, so let me quickly summarize what I've described so far. Yes, there's a question at the top there.
Sorry, did you have any disturbances in these experiments?
So there were no external disturbances, so there was no wind or anything like that. But I was taking into account the parametric uncertainty in the model itself that came from the fact that I had a finite amount of data that I was using to fit my model. Okay, so I've described these computational techniques, specifically sums of squares programming, to compute funnels, which allows us to reason about the nonlinear dynamics of the system and also uncertainty in the dynamics. So I presented these hardware experiments on a small fixed-wing airplane. And one of the things I was slightly surprised by was that sums of squares programming was actually able to handle this kind of 12-dimensional system. So I mentioned that the 8JB techniques typically have trouble scaling up beyond about 5 or 6 dimensions unless you do something special. And when I first started working with sums of squares, I wasn't sure if it would be able to handle this kind of dimensionality. So I presented these experiments for validating that the computational guarantees that we computed actually translate onto the real hardware system. And there's a couple of things I want to point out here. So I mentioned that these computational techniques have been pretty widely used in the controls literature for doing Lyapunov analysis. But there's been very limited amount of work on actual hardware implementation and validation of these techniques. So as far as I know, these experiments that I presented today and another set of experiments that I did a couple of years ago are the first to do this kind of thorough hardware validation and implementation. And the other thing I want to mention is that even though many of these techniques are really well known in the optimization and controls communities, they're not so well known in the robotics community. So one of the contributions here is to introduce some of these tools to the robotics community and actually demonstrate that they make sense in robotics applications. Okay, so switching to the online or the real-time computation phase, again, the question is, how do you deal with obstacles that show up in front of the robot at runtime? So the basic idea is to search through a large pre-computed library of funnels and try to find one that's collision-free. So more precisely, what we want to do is find one whose projection onto the space in which the obstacles live, that projection is collision-free. So the nice thing about this is that it's purely a geometric problem. So we don't need to reason about the nonlinear dynamics or the uncertainty in the dynamics. All of that complexity is summarized within the geometry of the funnel. And we can also leverage some pretty mature software packages for doing this collision checking at real-time rates. So by real-time here, I mean approximately 50 to 100 hertz. So for example, the bullet collision engine, which is used in a lot of video game engines. Okay, so one question I haven't addressed yet is, what if we cannot find a collision-free funnel in our library? So one idea is to exploit invariances or symmetries in the dynamics. So for example, the dynamics of a UAV system are invariant to shifts in X, Y, Z, and also rotations in yaw. So what this means is we can take a funnel that we computed in some location in space and move this funnel around while still having the shifted funnel be valid for the system. But of course, we can't arbitrarily shift the funnel anywhere we want. We still need to make sure that the robot is actually able to execute the shifted funnel. So in other words, we still need to make sure that the current state of the robot is contained within the inlet of the funnel. But if you can find such a shift, then you're guaranteed that when you execute the shifted funnel, you'll remain collision-free. And it turns out you can search over a subset of these shifts using convex, quadratically constrained quadratic programming, which is a particular kind of convex optimization problem that, again, we can solve at real-time rates for this problem. Okay, so in the hardware experiments that I'm about to present, I had 40 different funnels computed along these trajectories that you see here. So in these experiments, the planner is not informed where obstacles in the environment are until the airplane clears the launcher. So as soon as the airplane clears the launcher, I tell it, here's a number of obstacles in front of you, and then it goes and does the search and reacts in real time. So here's a video with real obstacles. No, I'm assuming that that's not uncertain. Yeah. So the obstacles spell out MIT, by the way, in case you didn't notice. I was bored one day. Okay, so here are some examples of what the funnels look like for these different environments. So as you can see, they're all collision-free. And one thing that's really worth pointing out is the importance of doing this, exploiting these invariances or symmetries in the dynamics. So in particular with the environment with the hoop in it, you would have to get extremely lucky to find a funnel that fits exactly in between the hoop. But if you exploit invariances or symmetries, you can just shift the funnel out of collision and execute the shifted funnel instead. So being able to exploit these symmetries gives you a lot of expressivity in terms of your funnel library. Yes, go ahead.
I'm kind of trying to understand how difficult the problem is in terms of, like, you really want to push this technique to when it actually fails and see how sharp those boundaries are. Yeah. And, because maybe it's easy and, we didn't have to worry about safety here at all. And, like, do you have a sense in which is this thing actually breaking down at the boundaries of where it says it should break down, or are we well within the safety regime?
Okay, so I guess the question is, so I'm going to paraphrase again, but the question is essentially how tight these bounds are and whether we're pushing the system to the limit. So I've done some experiments where I start the airplane just a little bit outside the funnel, and in this case I see that it kind of remains along the boundary and it doesn't really go very quickly to the trajectory. So I think the funnels and these bounds that we're computing are pretty tight, and I feel like we're pushing the system to its limit, or close to its limit anyways. Yeah. Okay, so one question I haven't really addressed yet is what kinds of environments, so maybe this will also partially answer your question. So what kinds of environments can we guarantee to be able to find a collision-free funnel in? So let me make some really simple observations. So the first is that the obstacles cannot be too close to the airplane. So in this case, the airplane just won't have enough time to react. So the obstacles also cannot be too big. So we might not have a funnel in our library that goes all the way around a large wall, for instance. And finally, the gap between the obstacles also needs to be big enough for the airplane to fit through. So it turns out you can write down some pretty simple geometric conditions on the environment. So in particular, the distance to the obstacles, the size of the obstacles, and the distance between the obstacles, such that we can guarantee collision-free flight. And as you would expect, these geometric conditions depend on the geometry of the funnels in your library. And the basic idea is to write down these conditions such that there's always some gap in between the obstacles, such that there's some funnel in your library that fits through this gap. Okay, so far I've focused on this important subproblem of finding a single maneuver, but I want to now zoom out to the more general problem of flying continuously through some environment. So the first idea we can leverage is a pretty old idea in robotics, so it's called sequential composition. So two funnels are sequentially composable if the outlet of one fits completely within the inlet of the next one. So funnels are sequentially composable in this way, then you can essentially execute one after the other. So we can check this compatibility condition between funnels using a simple sums of squares program in an offline stage. And what this allows us to do is take some finite library of funnels and stitch them together in order to make richer motion plans. But of course, we still have this problem of having just a finite sensor horizon, so we can't actually see all the way through the environment, and we don't know where all the obstacles will be in that environment. So what do we do about this? So instead of presenting the formal algorithm, I think it's easiest to present the main idea with a video. So in the video that you'll see, the system is a quadrotor system, which has a 12-dimensional state space and 4 control inputs. And there's an uncertain crosswind that's blowing the quadrotor around in the horizontal direction. So the basic idea is to find a sequence of funnels that's collision-free for the environment that you can see. You then start executing the sequence, and you essentially replan as your sensors report more obstacles in the environment. So this kind of planning is essentially called receding horizon planning in the planning and controls literature. So here's a video without the funnels superimposed, so you can get a sense for what that looks like. And again, it turns out that you can write down some simple geometric constraints or conditions on the environment that guarantee that you'll always find a collision-free funnel when you do this replanning. So you can essentially fly forever through an environment that satisfies these geometric conditions. Okay, so again, quickly summarizing where we are so far. Yes, go ahead.
There's a difference between flying continuously and making some progress toward a goal.
Yeah.
Does that significantly increase the challenge here, or that's just a complication that's not worth discussing in the context of the talk?
Yeah, I think that's the latter. So actually, maybe I should repeat the question again. So the question is, taking into account a goal state or making progress towards some goal, is that significantly more complicated than flying continuously through some environment. So I think essentially these funnels can be thought of as motion primitives in the usual sense. And you can use heuristic planners just like you have heuristic planners in the usual motion planning or trajectory library literature to make progress towards a goal. I mean, there's simple ways of doing it. For example, you can bias your search towards funnels or maneuvers that make more progress towards the goal. And if you have a particular goal set that you want to go to, you can also potentially do the planning backwards. So you can fix the outlet and do a backward search. Yeah, so those are all potential options. Okay, so I presented this approach for doing real-time planning using funnels, which allows us to guarantee safe flight despite uncertainties if we're able to find collision-free funnels. So I presented hardware experiments on a small fixed-wing airplane, dodging obstacles in cluttered environments in previously unseen environments. And one thing that's worth pointing out is that often people associate robustness with extremely conservative behavior, but it might be slightly surprising that this isn't necessarily the case. So in the experiments that I presented with the fixed-wing airplane, the airplane is doing some really aggressive maneuvers while still being robust. So I described how we can fly continuously through some environment using this receding horizon planning approach. And finally, we can again write down geometric constraints on the environment that guarantee that a collision-free funnel will always be found. Okay, so far in this talk, I've focused on this problem of this domain of UAV flight. But again, I want to point out that this funnel library-based approach is significantly more general. So for instance, you might imagine using it for doing footstep planning on a humanoid robot, where the idea would be to pre-compute some large library of funnels that correspond to different footsteps and choose from this funnel library at runtime based on what the environment looks like. But there's a big question here, which is, can we scale our computations, so our funnel computations, to anything on the order of magnitude or on the scale of a humanoid robot? So this is the Atlas robot, which was used in the recent DARPA robotics challenge. And even really simplified models of these systems can have as many as 30 dimensions in their state space. So this last technical section is joint work with Amir Ali Ahmadi from Princeton University. Okay, so before addressing this challenge of scalability, let's first understand where the computational limits of sums of squares programming actually come from. So here's a quick reminder. So a polynomial P is a sum of squares if and only if you can write it down in this form. So where V was this vector of monomials, and Q is a positive semidefinite matrix that you're searching for. So it turns out it's really this positive semidefiniteness constraint, or PSD constraint, that's really expensive. So as the dimensionality of your problem grows, so as the number of variables in X grows, and also as the degree of your polynomial grows, the size of this matrix grows very rapidly. So if you were doing Lyapunov analysis, for instance, on a degree 3 polynomial system in 20 variables, then you would have more than 1 million decision variables in your optimization problem. And imposing this PSD, positive semidefiniteness constraint, gets very expensive very rapidly. So there's been a lot of really interesting work trying to address this challenge of scalability. So for instance, a number of techniques for exploiting special structure, such as symmetry or sparsity in your problem, and also customized algorithms for many classes of problems, such as first-order methods, for example. So the approach that we've taken is somewhat different. So our approach is essentially not to work with the sums of squares polynomials to begin with. What we do instead is give other sufficient conditions for polynomial non-negativity that are stronger than sums of squares, but significantly cheaper. So one way to think about this is that we're essentially searching over a subset of the SOS, the sums of squares polynomials, but that these subsets are much more tractable to optimize over. So we might lose something in terms of conservatism, but we gain a lot in terms of scalability. Okay, so how do we actually search over these subsets? So the basic idea is to replace this expensive PSD, positive semidefiniteness constraint, on the matrix Q with something stronger, but a lot cheaper to impose. So we proposed a number of different conditions. I'll describe just a couple of them here because they're particularly nice. So the first condition is diagonal dominance. So matrix Q is diagonally dominant if for every row in the matrix, the diagonal element is greater than or equal to the sum of the absolute values of the off-diagonal elements. So essentially, for each row in the matrix, the diagonal element dominates the off-diagonal ones. So it turns out you can impose this condition just using linear programming constraints. So the second condition is scale diagonal dominance. So matrix Q is scale diagonally dominant if you can scale it with a positive diagonal matrix such that the product is diagonally dominant. And it turns out you can impose this condition using second-order cone programming. So this leads to two classes of polynomials, which we call the DSOS and the SDSOS polynomials, when you do this replacement from PSD to DD or STD. So the really cool thing here is that both linear programming and second-order cone programming are significantly cheaper than semi-definite programming. And for those of you in the audience who are experts on sums of squares programming, so you might be familiar with some really deep results from real algebraic geometry on the gap between sums of squares and non-negative polynomials, and how you can close this gap using multiplier polynomials. So many of these same results also go through in the DSOS and the SDSOS settings, but I won't say too much about that here. Okay, so going back to the original question I started off with, so can we scale our computations to anything on the order or scale of a humanoid robot? So I applied this DSOS and SDSOS programming techniques to design a balancing controller for the Atlas robot on its toe. So I considered a slightly simplified model of the system, which had 30 dimensions in its state space and 14 control inputs. So the physical parameters, such as the geometric or the inertial parameters of the model, are realistic. But one simplification that I'm making is that there's a pin joint at the interface between the foot and the ground. So more specifically, what I'm doing here is simultaneously searching for a Lyapunov function and a feedback controller in order to maximize the size of the region of attraction for the controller. So essentially the set of initial conditions from which the controller is able to stabilize the system. And it's worth pointing out that this problem is way beyond what sums of squares programming can handle. So here's a video of what the controller looks like. So this controller was designed using SDSOS programming, which is the second-order cone programming version. So what I'm doing here is randomly sampling different initial conditions and simulating the feedback controller from these different initial conditions. So you can imagine that the robot is being perturbed at each of these trials. And as you can see, it's able to stabilize a pretty wide range of different initial conditions. Okay, so we propose these scalable alternatives to sums of squares programming, which are based on linear and second-order cone programming instead of semi-definite programming. So this has allowed us to scale to problems well beyond what SOS programming can handle. So in this talk, I described this 30-dimensional and 14 control input model of the humanoid robot. But in other work, we've applied this technique to many other problems in different domains. So other problems in control, problems in machine learning, finance, optimization. And each of these cases, we've seen some really significant gains in terms of the scalability without too much of a loss in terms of the optimal value or the conservatism we get with this approach. And I think there's some really exciting potential for real-time applications of this approach. So for higher dimensional systems, we get this gain in terms of scalability. But I think for lower dimensional systems, there's an opportunity to do real-time computation with these approaches. So maybe real-time computations of feedback controllers or funnels even. And I think that's a really exciting potential direction. Okay, so I believe that the approach that I presented has a lot of potential for being applied on robots to make them operate safely in real-world environments. But I think there's still a lot of work that needs to be done. So in the last few minutes, let me just highlight some possible future directions. So the first research question is how can we augment some of these formal or model-based tools that I've described in this talk with data-driven or learning-based approaches. So hopefully I've convinced you that these model-based techniques can be extremely powerful. But at the end of the day, all models, even when you include uncertainty, are only approximately valid on the real system. But I think there's a big opportunity in terms of the vast amounts of data we can collect from real-time operation of the system. And the question is how can we take this data and augment some of our model-based or formal tools. So one possible approach is just to make local adjustments to the dynamics of the system using this data. But a potentially more interesting approach is to make local adjustments directly to the funnels themselves. So here's a picture of what that might look like. So let's say you computed a funnel using some nominal model of your dynamics of the system. But in reality, you found that there was some unexpectedly large wind gust that blows the airplane off this, out of this funnel. So the idea would be to update this funnel in such a way that the updated funnel is consistent with the new piece of data that you saw. And the basic idea would be to do this iteratively as you collect more data. So in general, I believe that really successful robotic systems of the future will have a really strong model-based component, but will also augment some of these model-based techniques with data-driven or learning-based approaches. So another question I haven't really addressed in this talk yet is the question of sensing. So how can we sense or do obstacle detection in real time? So there's been some really exciting work on fast stereo vision. So for example, using FPGA or even doing sparse versions of stereo. So I think doing obstacle detection in real time is becoming feasible. But I think from a research perspective, a really fascinating question is, do we even need accurate geometric representations of the world in order to be able to navigate it? So in practice, relatively simple sensing strategies can work quite well. So there's an example from EPFL that I particularly like, where they had this array of optical mice, so the same kind of sensor your computer mouse uses to measure optic flow in about these 7 or 8 different directions. So it's very sparse and simple kind of sensing. But they were able to use it to do this kind of cool obstacle avoidance that you see in the video here. So one research question is, can we make the same kinds of guarantees that I was describing in this talk with these very simple sensing strategies? So I think this has the potential to be not only much more computationally efficient, but also potentially much more robust in terms of sensing uncertainty. So instead of trying to accurately measure or represent the environment very accurately geometrically, if you know what quantities are really of interest and you measure these quantities very accurately, this might be much more robust sensing uncertainty. Even more broad and general question is, what should we sense or estimate? So I think these are really exciting times in robotics, where there's a new sensor that comes out essentially every couple of months. But this begs the question, what do we really need to sense or estimate in order to be able to achieve the task that we're trying to accomplish? So I think a really fundamental open problem is coming up with a general approach for what you might call task-relevant estimation and control. So the question is, what are the minimal informational requirements for a given task? How do you extract this information from the sensors that you have, and then still be able to guarantee that you'll achieve the task that you're trying to achieve? So I think a general approach to this problem can have a huge impact on the robustness of our robotic control systems and get us a lot further along this dream of having robots operating safely in real-world environments. So I'd like to thank my collaborators and also a number of people I've received really useful feedback from over the course of this work, and also a number of different funding agencies. So I'll leave you with this contribution slide and take any further questions you might have.
There are questions, yeah.
Great talk, Ani. Looks like you're having a lot of success for situations where the dominant kind of uncertainties in the system, like your robot itself, and the environment is relatively benign.
Right.
So I wonder if you could talk a little bit about situations, what you do in situations, or how you see this extending to situations where the dominant source of uncertainty really is in the environment, and you're not able to kind of collect a bunch of data and offline.
Right.
Yeah, sure. I'll just repeat the question again. So the question is, so in the work that I presented today, the dominant source of uncertainty was essentially modeling uncertainty. But the question is, if you have external disturbances which are much more dominant, what are some of the approaches there? So if you have a worst case bound on the external disturbances, of course you can apply the approach directly. But I think one slightly different approach still related would be to make probabilistic guarantees instead of these worst case guarantees. So if you have a probabilistic model of wind gusts, for example, I think you can adapt some of these computational techniques to make probabilistic guarantees. So saying things like, I'll remain within the funnel with at least 95% probability. And there's been some work using Sundar squares to make those kinds of guarantees also. So that's one potential modeling approach. So I think a slightly different approach is instead of knowing your probability distribution, if you just know certain qualitative properties of your disturbances, so for example, if you know the moments of your distribution, you could try to do worst case analysis over all possible probability distributions that satisfy these moment constraints. So I think that might be also a promising modeling approach.
So you mentioned spending a lot of time doing system
Yep.
identification.
Uh-huh.
So I'm curious about what's the space of models and
Sure.
parameters you were searching in.
Sure.
And as a follow-up, what's the hope for automating that part?
Okay, yeah. So the question is, so I spent a lot of time doing system identification. What were the parametric models that I was searching over, and can you automate this process? So I'll describe the process that I went through. So what I first did was just went to a standard aerodynamics textbook, looked at the parametric model. So as I mentioned, I was essentially treating the system as a rigid body subject to aerodynamic forces. So I started off with a flat plate model of the system to begin with. And what I did initially was lots of isolated experiments to figure out what the parameters were. So for instance, I hung the airplane from a digital scale and measured the relationship between the throttle command and the amount of thrust produced. So I also took an anemometer and measured the relationship between the throttle command and the speed of the prop wash. So a lot of isolated experiments like that. So in terms of and then at the end, I collected lots of data with open loop control inputs, and I did simulation error minimization to refine the parametric model. So in terms of parameters that I was searching over, or that I was searching over, so one big thing was the lift and drag coefficients as a function of the angle of attack. So I actually did a lot of experiments where I was just throwing the airplane as a glider, and you can actually back out what the lift and drag coefficients are at each instance in time if you can measure accelerations. So I fit correction terms to those lift and drag profiles. So yeah, automating that process, I think you can probably do that to some extent. But the hard thing is knowing what the different parameters are and what parametric structures you should be searching over. So one other thing that I didn't mention is there's also a significant amount of delay in the system. So there's about 45 milliseconds of delay. So if you did your system identification without taking that into account, your results would not be very good. So I think that's where some intuition comes in, and it's hard to kind of automate that.
So could you theoretically or experimentally measure the loss from solving diagonal dominant systems as opposed to SOS systems?
Yeah, sure. So the question is, can we empirically measure the loss or the conservatism we get when we go to these LP and SOCP versions of sum of squares? So actually I have a backup slide maybe that I can use. Yeah, so the system here is a n-link pendulum. So I'm making the system balance about the upright. So there's no actuation at the bottommost joint, but there's actuation everywhere else. And there's a LQR controller that's making it balance. And I'm trying to find the region of attraction basically for the system. So in this case, so I won't go through the running times, but the optimal values we can compare for lower dimensional systems where we can actually run the sums of squares program. So what I'm plotting here is two projections of the regions of attraction we get onto two different subspaces. So in the blue is the region of attraction we get with sums of squares. The green is what we get with the SOCP version, and the red is what we get with the LP version. So the green is actually, so the SDSOS version is very close to what we get with the SOS version. And you can see it's about 80 to 90% of the optimal value. So the LP version is a little bit more conservative, but still potentially useful in practice. So yeah, in many problems that we've seen this kind of behavior where the SOCP version is pretty good compared to the SOS version. The LP version is a little bit more conservative. But the running times are actually about the same for the LP and SOCP versions.
You see Shane's question and the broader question of conservatism, like in a simulator, you could try the same thing and actually see when it breaks. Like you're showing this example of when it succeeds.
Yeah.
You can push it to where it breaks and see. Like, do you have an idea what's breaking on a more challenging problem? And you don't have to worry about destroying your plane or whatever.
Yeah, sure. So again, in terms of measuring conservatism, essentially in simulation. Yeah.
The standing robot you had.
Okay, yeah, I've done some of that. It's really hard to do for a really high-dimensional system. So we've done it for lower-dimensional system where you sample initial conditions from slices, and you see what the number of points are which get to your goal set, for example. And it's not super conservative, actually. I don't have a picture here.
Is it hard to do? Why can't I just like pick some starting condition and just keep making it more and more extreme?
Sure.
See when it breaks.
Yeah, sure. I just meant it's hard to cover the set of. Yes, correct. Yeah, so that kind of thing I've done, and at least in the examples that I've tried it out on, it's not extremely conservative. Yeah.
Okay, I think we are right on time.
All right.
Thanks a lot.
Thanks very much.